Advanced NDT for stainless steel cladded carbon steel, innovative inspection methods ensuring material integrity. Introduction to NDT challenges in stainless steel cladded carbon steel, inspection challenges due to dissimilar metal cladding, limitations of conventional ultrasonic testing, primary inspection method, phased array ultrasonic testing, PUT applications, disbonding, welds, and corrosion mapping, advanced PUT imaging, total focusing method, TFM, time of flight diffraction, TOFD, for weld defect sizing, surface inspection using liquid penetrant testing, PT, eddy current testing, ECT. For near-surface evaluation, recommended NDT strategy and key engineering considerations. Stainless steel cladded carbon steel is widely used in pressure vessels, pipelines, and process equipment where corrosion resistance is required at a lower cost than solid stainless steel construction. While this material combination provides excellent service performance, it introduces significant inspection challenges, particularly when non-destructive testing is required to assess structural integrity without impairing operation. The most critical degradation mechanisms include cladding disbonding at the interface, weld defects within the cladding or overlay welds, and corrosion or wall loss in the carbon steel substrate. These damage modes are often hidden from visual inspection and cannot be reliably detected using basic surface techniques alone. From an engineering perspective, inspection methods must be capable of penetrating complex, dissimilar metal interfaces while providing sufficient resolution to detect small but critical defects. The austenitic stainless steel cladding exhibits coarse, anisotropic grain structures that scatter and attenuate ultrasonic energy, making conventional ultrasonic testing unreliable. As a result, advanced ultrasonic techniques are required to ensure inspection reliability, fitness for service assessments, and compliance with codes such as ASME, API, and ISO standards. This presentation focuses on the most effective and proven non-destructive testing methods for these applications, emphasizing advanced ultrasonic testing. Particularly phased array ultrasonic testing, PUT, and time of flight diffraction, TOFD, supported by complementary surface inspection methods. The goal is to provide an engineering-focused inspection strategy that balances detection capability, accuracy, and practical field implementation for cladded steel components in critical service. Illustrative schematic showing a carbon steel base material with a stainless steel cladding layer, highlighting the critical bond interface where disbonding may occur. The primary inspection challenge in stainless steel cladded carbon steel arises from the metallurgical differences between the two materials. Carbon steel is generally isotropic and fine-grained, allowing ultrasonic waves to propagate predictably with minimal scattering. In contrast, austenitic stainless steel cladding has a coarse, columnar grain structure formed during welding or roll bonding, which causes significant beam skewing, attenuation, and noise. This anisotropy disrupts traditional ultrasonic assumptions related to sound velocity and beam direction, often resulting in false indications or missed defects when using conventional single-element ultrasonic testing. Furthermore, the most critical defect of concern, cladding disbonding, occurs at the interface between the two materials and may present as a very thin, planar separation that produces weak reflections. Detecting such defects requires precise beam control, focusing, and multiple inspection angles. Surface condition is another factor. Cladding surfaces may be rough, work-hardened, or exhibit weld ripples that complicate probe coupling and signal interpretation. From an operational standpoint, inspections are often performed on in-service equipment with limited access, complex geometries, or elevated temperatures. These factors necessitate advanced, flexible inspection techniques that can adapt to geometry while maintaining accuracy. Understanding these challenges is essential for selecting appropriate NDT methods and designing procedures that provide reliable, repeatable results suitable for engineering decision-making. Conceptual image representing ultrasonic beam distortion and scattering when propagating through anisotropic stainless steel cladding. Conventional ultrasonic testing, typically using single-element straight beam or angle beam probes, has long been a standard inspection method for carbon steel components. However, its effectiveness is significantly reduced when applied to stainless steel cladded materials. Single-element probes generate a fixed beam angle and focal point, limiting the inspector's ability to interrogate complex interfaces or orient the beam optimally for defect detection. In anisotropic cladding, the ultrasonic beam can refract unpredictably, leading to inaccurate depth sizing and location errors. Additionally, the signal-to-noise ratio is often poor due to grain noise, making it difficult to distinguish real defects from structural noise. Conventional UT also lacks the capability to generate comprehensive images of the inspected volume, relying instead on A-scan signal interpretation, which is highly operator-dependent. This increases the risk of missed indications, especially for planar defects such as disbonding or lack of fusion in weld overlays. For corrosion mapping, conventional UT provides only point thickness measurements, offering limited coverage and increasing the likelihood of localized wall loss being overlooked. From an engineering risk perspective, these limitations can result in non-conservative assessments and unplanned failures. Consequently, while conventional UT may still have limited use for preliminary screening, it is not suitable as a primary inspection method for critical stainless steel cladded components. Simplified depiction of single-element ultrasonic testing showing limited beam coverage and lack of steering capability. Phased array ultrasonic testing, PUT, is the preferred and most effective method for inspecting stainless steel cladded carbon steel. PUT uses probes consisting of multiple individual elements, typically ranging from 16 to 128 elements, which are electronically pulsed with precise time delays. This allows the ultrasonic beam to be steered, focused, and swept through a range of angles without physically moving the probe. For cladded materials, this capability is critical, as it enables inspectors to compensate for anisotropy and interrogate the cladding-to-base metal interface from multiple orientations. PUT provides real-time two-dimensional and three-dimensional imaging, such as S-scans and C-scans, allowing engineers to visualize internal structures and defect morphology. This imaging capability significantly improves defect characterization, sizing, and confidence in interpretation. PUT is particularly effective for detecting lack of bond or disbonding at the interface, internal weld defects such as lack of fusion, slag inclusions, and porosity, as well as general wall thickness measurement. From a practical standpoint, PUT inspections can be automated, improving coverage, repeatability, and data traceability. The recorded data can be reviewed and analyzed offline, supporting quality assurance, audits, and engineering assessments. These advantages make PUT the cornerstone of any robust inspection strategy for stainless steel cladded components. Illustration of phased array beam steering and focusing used to inspect cladding interfaces and weld regions. PUT is highly versatile and can be applied to multiple inspection objectives within stainless steel cladded carbon steel systems. For disbonding detection, straight beam pulseco PUT techniques are typically employed from the carbon steel side, where ultrasonic propagation is more predictable. This approach maximizes sensitivity to planar separations at the cladding interface. For weld overlay inspections, angle beam PUT scans allow comprehensive coverage of the weld volume, enabling detection of lack of fusion, cracks, and inclusions. The ability to sweep through multiple angles ensures that defects of various orientations are detected. In corrosion assessment, automated PUT systems can generate high-resolution C-scan maps that provide a detailed thickness profile over large surface areas. This is particularly valuable for identifying localized corrosion or erosion that may not be detected with spot measurements. From an engineering standpoint, these thickness maps support remaining life calculations, corrosion rate analysis, and fitness for service evaluations. The integration of multiple inspection objectives into a single PUT campaign improves efficiency while maintaining high data quality. As a result, PUT is not only a defect detection tool but also a powerful asset for asset integrity management and long-term maintenance planning. Example representation of a PUT corrosion C-scan showing wall thickness variations across a cladded surface. The total focusing method, TFM, represents a significant advancement in ultrasonic imaging and is increasingly applied to complex cladding inspections. TFM is based on full matrix capture, FMC, where each probe element transmits sequentially while all elements receive, resulting in a complete dataset of ultrasonic responses. Advanced algorithms then focus the ultrasonic beam at every point within the region of interest, producing high-resolution images that approach radiographic quality. For stainless steel cladding, TFM is particularly valuable because it enhances signal clarity and defect definition in highly anisotropic materials. This improved resolution allows for accurate detection and sizing of small, complex defects such as microcracks, clustered porosity, and irregular disbonding. From an engineering reliability perspective, TFM reduces uncertainty in defect characterization and improves confidence in acceptance or repair decisions. While TFM typically requires more computational power and careful setup compared to standard PUT, its benefits in critical applications often justify its use. As inspection technologies continue to evolve, TFM is becoming an essential tool for high-integrity components where conventional methods may be insufficient. High-resolution ultrasonic image illustrating the enhanced defect clarity achievable using total focusing method. Time-of-flight diffraction, TOFD, is a specialized ultrasonic technique that complements PUT, particularly for weld inspection and crack sizing. Unlike pulse-echo methods, TOFD relies on the detection of diffracted ultrasonic waves generated at the tips of defects. This makes TOFD highly accurate for through-wall sizing of cracks, regardless of their orientation. In stainless steel cladded carbon steel systems, TOFD is commonly used to inspect weld overlays and structural welds where accurate defect height measurement is critical for fitness for service assessments. When used in combination with PUT, TOFD provides independent verification of defect presence and size, reducing the likelihood of false calls. While TOFD alone may be less sensitive to very shallow defects or disbonding at the interface, its strength lies in precise sizing of planar flaws. From an engineering assessment standpoint, this accuracy supports fracture mechanics evaluations and remaining life predictions. The combined use of PUT and TOFD is widely recognized as best practice for critical weld inspections in demanding service environments. Schematic depiction of TOFD probe arrangement and diffracted signal detection from weld defects. Liquid penetrant testing, PT, also known as dye penetrant inspection, DPI, is an essential complementary method for stainless steel cladded components. PT is specifically designed to detect surface-breaking defects such as fatigue cracks, pinholes, and porosity that may not be detectable by ultrasonic methods. In cladded systems, surface defects can act as initiation points for corrosion or cracking, making their detection critical for long-term integrity. PT is highly sensitive, relatively simple to apply, and well-suited for stainless steel surfaces due to their non-porous nature. From an inspection planning perspective, PT is often performed after ultrasonic inspections to ensure comprehensive coverage of both internal and surface-related damage mechanisms. However, PT requires proper surface preparation and cleaning, as well as post-inspection removal of chemicals, which may limit its use in certain operational environments. Despite these limitations, PT remains a valuable tool for confirming surface integrity and supporting overall inspection confidence. Example of liquid penetrant indications highlighting surface-breaking defects on a stainless steel cladding surface. Eddy current testing, ECT, is an electromagnetic inspection technique that is particularly effective for detecting surface and near-surface defects in conductive materials such as stainless steel cladding. ECT does not require direct contact or liquid couplants, making it suitable for applications where cleanliness or accessibility is a concern. In cladded carbon steel systems, ECT is commonly used to identify surface cracks, measure cladding thickness in localized areas, and detect material degradation just below the surface. Its high sensitivity to small discontinuities makes it a valuable supplement to ultrasonic and penetrant testing. However, ECT has limited penetration depth and is generally not suitable for detecting deep internal defects or interface disbonding. From an engineering inspection strategy standpoint, ECT is best applied as a targeted tool for specific surface-related inspection objectives, particularly in areas where PT may be impractical. When used appropriately, ECT enhances overall inspection coverage and reduces the risk of undetected surface damage, conceptual illustration of eddy current probe interaction with surface and near-surface defects in stainless steel cladding. An effective NDT strategy for stainless steel cladded carbon steel must be based on a clear understanding of damage mechanisms, material behavior, and inspection objectives. PUT should be selected as the primary inspection method for detecting disbonding, internal weld defects, and corrosion mapping due to its superior imaging capability and adaptability to anisotropic materials. For critical applications requiring enhanced resolution, PUT with total focusing method provides additional confidence in defect detection and sizing. TOFD should be used as a complementary technique for accurate weld crack sizing and validation of PUT results. Surface inspection methods such as liquid penetrant testing and eddy current testing play a crucial supporting role in identifying surface breaking and near-surface defects. Key considerations include proper surface preparation, inspection from the carbon steel side where feasible, and the use of representative calibration blocks with artificial defects to validate procedures. Scanning direction, probe selection, and data interpretation must be carefully controlled to ensure reliability. By integrating these techniques into a structured inspection program, engineers can achieve a high level of confidence in integrity assessments, support fitness for service evaluations, and optimize maintenance planning for critical cladded assets.